All right, let's jump right into this explainer with a fun question for you. Have you ever actually wanted to build your own dancing water fountain? You've probably seen those massive, perfectly synchronized water shows in big city parks or in front of grand hotels, where the water flawlessly choreographs itself to the soaring peaks of a symphony or the heavy bass of a pop song. They seem like pure magic, right? Or at the very least, multi-million-dollar engineering marvels. But what if I told you that the core principles behind that massive spectacle can fit right onto your desk?
Welcome to The Explainer, where we demystify the engineering behind all this. We're going to take what looks like a really complex mix of power electronics, sensors, and code and turn it into a super approachable DIY project. Today, we're diving into the exact mechanics of an Arduino-controlled musical water fountain. We'll be pulling from engineering journals, maker forums, and simulation tutorials to see exactly how these systems are designed from the ground up.
To make sure this build is a success, we're going to follow a structured builder's journey today. First, we'll look at the musical fountain dream, then powering the pump safely, sensing the musical beat, decoding audio with FFT, and finally, some simulation and troubleshooting tips.
So let's start with Section 1, the musical fountain dream.
Our ultimate goal here is pretty awesome. We want to create an innovative fountain that takes external audio from a source, like your smartphone, maybe an iPod or a PC, and physically responds to it. It sprinkles water and flashes LEDs to the exact beats and rhythms of your favorite song. It's not just randomly shooting water into the air, it's a dynamic system that is literally listening to the music and reacting in real time. The Arduino Nano basically acts as the conductor of this tiny orchestra, translating invisible sound waves into physical movement.
Moving on to Section 2, powering the pump safely. Now, there is a classic cautionary tale straight from the engineering forums that we absolutely need to talk about. We see rookie makers try to power a standard 12-volt DC water pump with a tiny BC547 transistor all the time. Bad idea. While that pump might only use about half an amp while running smoothly, DC motors have this thing called a startup spike or stall current. Literally, at the exact millisecond you switch it on, it pulls many, many amps. If you use a fragile component like a BC547, that massive current spike is going to fry the silicon instantly. So to avoid frying your components, you've got to upgrade your hardware to handle that heavy electrical lifting. Instead of that fragile little transistor, you need a robust logic-level MOSFET, like an IRL 520. They're highly efficient and won't overheat on you. Or alternatively, you could use a dedicated 12-volt relay module. A relay is essentially just an electromechanical switch. Your Arduino sends a tiny 5-volt signal to the relay, which then safely clicks a physical switch closed, allowing the completely separate 12-volt power supply to rush into the pump. It neatly keeps the high-power muscle completely isolated from the low-power brain. And here is where our ultimate safety net comes into play. Whenever you're working with DC motors or relays, you're dealing with inductors. What happens when you suddenly cut power to a spinning pump? The magnetic field collapses and it generates this dangerous spike of reverse voltage that shoots right backwards through your circuit. Yikes, right? So you must always include a freewheel or flyback diode, something like the 1N40001, placed in parallel with your load. This diode acts as a one-way pressure valve, safely looping that nasty voltage spike back into the motor itself and protecting your delicate Arduino from being absolutely destroyed. All right, let's jump to Section 3, sensing the musical beat. For basic setups, makers typically use a simple sound sensor module. But if you look at troubleshooting forums, a huge common issue is getting either zero readings or constant, non-stop triggering. The trick to fixing this is actually super tactile. You just have to tweak the little blue potentiometer on the sound sensor module itself. This tiny screw is absolutely essential for setting the perfect sensitivity threshold. If you set it too high, your fountain is just going to spray water at the low hum of your refrigerator. Set it too low and you could shout at it and nothing would happen. You really have to dial it in for your specific room environment.
Let's quickly break down how this sensor actually does its job. The electric microphone right at the front captures the physical sound wave and converts it into a tiny electrical signal. But because this signal is incredibly weak, it gets fed into an onboard LM393 operational amplifier, which basically acts as a comparator. It constantly compares the microphone's incoming signal against that exact threshold you just set with the blue potentiometer. When a loud beat hits and actually exceeds that threshold, the op-amp outputs a simple, clean digital high to the Arduino. When the music drops and it gets quiet, it outputs a digital low. It neatly translates complex audio into a simple on and off language the Arduino can easily read.
Which brings us to Section 4, decoding audio with FFT. Now, if you want to build a more advanced fountain, the whole system architecture completely changes. Instead of just having a microphone passively listening to the room, audio signals from a smartphone or an MP3 player are first amplified using an LM386 IC, and then transferred directly into an analog input pin on the Arduino itself. From there, the Arduino processes that signal and uses its digital output pins to control multiple DC pump motors and LED systems. But wait, how does the Arduino actually know the difference between a high-pitched violin and a low, thumping bass drum?
So the math that makes this absolute magic possible is called the fast Fourier transform, or FFT for short. You can really think of the FFT as a mathematical prism. Just like a physical glass prism takes a single beam of white light and shatters it apart into a rainbow of individual colors, the FFT takes a single, messy audio wave and breaks it down into a perfect rainbow of individual, isolatable frequencies.
Here's exactly how the Arduino pulls off this mathematical heavy lifting. First up, it samples the incoming audio using its analog-to-digital converter. Then, it unleashes the FFT algorithm. This algorithm operates at a ridiculously efficient O(n) log n processing speed, allowing it to decompose that audio sequence into distinct frequency bins. Because it can now mathematically isolate the heavy bass frequencies from the high treble frequencies, the Arduino can assign them to entirely different water jets. So think about it. When the bass drops, the center jet shoots high, and when the hi-hats tinkle, the outer LEDs flash. It creates a truly dynamic, multi-layered show.
But you guessed it, there's a catch. Audio moves fast, really fast. So to process it without missing a single beat, you actually have to turbocharge the Arduino's internal clock. Out of the box, the Arduino's analog-to-digital converter is just a little bit too slow for high-quality audio. It runs with a default prescaler of 128. But by dropping that prescaler all the way down to 32 right in your code, you drastically boost the ADC clock speed. We're talking sampling the audio at a blistering 38.4 kilohertz. This is what ensures your fountain reacts instantly, perfectly locked in time with the music.
And finally, Section 5, Simulation and Troubleshooting Tips.
So when you're using simulation software like Proteus to test all this out before getting anything dangerously wet, you can't exactly just clap your hands at your computer monitor to trigger a virtual microphone, right? Instead, engineers use this really clever workaround. Step 1, you just load your compiled code, your hex files, straight into the virtual Arduino and sound sensor modules. Step 2, you connect a logic state module directly to a special test pin on the virtual sensor. And Step 3, you simply click that module to toggle between a 0, meaning no sound, and a 1, meaning sound detected. This lets you safely debug your code, make sure your relays are firing at the exact right time, and check your entire digital logic on screen before you build the actual physical circuit.
Wow, okay, we've covered a massive amount of ground today. We started with the dream of a dancing fountain, figured out how to safely provide muscle to the water pumps using relays and flyback diodes, gave the whole system senses using an electric mic, and then finally unlocked its brain by using fast Fourier transforms to turn a messy audio wave into distinct, controllable beats. So now that you are fully armed with the knowledge of the muscle, the senses, and the brain to build this incredible project, what song will your fountain dance to first? Think about it, and until next time, keep exploring.